For as long as people have inhabited the earth, they've wondered about the elements and the source of their power. What kind of enormous creative force lies behind creation? Who is the author of the thundering earth, with its whirling winds and roaring waters that cover most of its surface? As God's handiwork is revealed, we can but observe and wonder at the power and majesty of the awesome forces of God's creation. Hello, I'm Jim Pemble, your guide for this exciting series about the powerful forces of creation at work in the world around us. In the next hour, we're going to witness the weather, unleashed in its mightiest forms, and see some of the most dramatic storm footage ever gathered by both curious scientists and other weather observers. We'll learn about the dynamics of the weather around the globe and how the planet continually generates unimaginable atmospheric energies every minute of the day. We'll discover how hurricanes and tornadoes are born and find out more about the science and the art of weather forecasting. We'll also learn that no matter how good we are or ever get at tracking and predicting weather, it will always bring us into direct contact with one of God's most awe-inspiring sources of uncontrolled energy. Join me now as we explore the Earth's weather and experience the great maelstroms that shape our atmosphere, sweeping across the face of the planet. Get ready, you're about to be carried aloft around the globe on its whirling winds. Weather is at the heart of everything we do. The success or failure farmers have at growing our food, our ability to navigate the oceans, skies, and across the land, where and how we build our cities, the kinds of occupations we choose, the way we dress each day, all are fundamentally determined by the weather. What drives this great machine of wind and water? And how is the weather made?
I think that the power of storms is kind of, in a sense, a humbling experience. It shows you that you are a human being and that there is someone a lot greater than you that has a lot more power than you. I think it makes you realize, too, that you really do need to put control in your life into God, because obviously there's there's a lot of power that He has over your life. I think, too, the power of wind and rain is so indescribable and can sometimes be so tremendous and so awesome that it's something that many people just, they have no explanation for it other than, that someone else, something greater than us must be creating it.
We live at the bottom of an ocean of air 50 miles deep. This bubble of transparent gas is as thin as a sheet of paper relative to the size of our globe. The air is never still. Its layers, troposphere, stratosphere, mesosphere, and thermosphere, continually move in streams, whirlpools, eddies, and swirls. There are several reasons why. First, the planet itself is spinning, which sets the air in motion. Different currents of air travel at different speeds, sliding along next to one another, ruffling each other's edges.
The driving force of the weather is the sun. It provides the heat that gets the whole atmospheric engine running. It typically shines near the equator, varies a little bit where the maximum is, and of course there's very little sun at the poles. So you have this tremendous heat source along the equatorial regions of the globe and very cold source in the poles. We have the atmosphere always trying to reach a balance, and you can see already we have an imbalance with the cold north and the warm at the equator. So what happens is you try to get the warm pushed north and the cold pushed south. Well, when the Earth is rotating, that adds a new spin on things, so to speak. And that combination of the balancing forces and the spin of the Earth is what really creates our weather.
What we experience here as weather, then, begins out there 93 million miles away. It's the sun's energy, along with the motions of a spinning globe, that act as a catalyst, putting the wind and water of the world into motion. Heat from the sun evaporates water from oceans, lakes, and rivers. This warm, moist air tends to rise, while cooler, dry air sinks back to the surface. As the moist air gathers in the cold upper atmosphere, tiny ice particles form and coalesce into clouds. When they're saturated beyond their capacity to hold more moisture, the clouds rain back their water onto the land and into the sea. Working in concert with the cycle of evaporation, condensation, and precipitation, as well as the earlier factors we examined which influence the flow of air around the globe, is the tendency of air to spiral into areas of low pressure and out of areas of high pressure in a never-ending search for equilibrium in the atmosphere.
High pressure is basically an area where you have anticyclonic flow, or flow that's basically clockwise. And in high pressure areas you have sinking air, and so that weight of that sinking air at the surface is what creates a high pressure. In a low pressure area you have cyclonic circulation or counterclockwise circulation, and air is moving into a low at the surface and then rising up. And the low pressure areas is where we find all of our weather, or most of it, because that rising air cools as it rises, and that is really the mechanism behind cloud formation and precipitation formation, is that cooling process. A very simple way of looking at that is that cooler air can hold less water than warmer air. So if you take a warmer parcel of air at the surface, lift it up and cool it, eventually it's going to come to a saturation point because it can hold less, that cooler air can hold less water. And if you continue to lift it, the water will continue to conglomerate into droplets, and the droplets will adhere together and become heavy enough to fall out of a cloud.
Temperature, motion, moisture. These are the basic characteristics that define the Earth's weather, especially the storms. But what is it that makes an ordinary rainstorm become one of the many types of powerful weather events, cyclones, typhoons, hurricanes, and tornadoes, that send us scurrying for shelter when we know they're on their way?
We saw the tornado in the distance, and when it got closer we went to the cellar, and when we could hear and feel that the wind had slowed down, we came out, and it was a little bit northwest of us, and where the main part of it, I'd say the eye of it, was about a mile from our house, and it was the most fearful looking thing that I had ever seen in my life. There were streaks of red and green, light red and light green streaks in with the blue and light color, and you could see the whirling of it, and it was making a lot of noise.
A typical thunderstorm releases 125 million gallons of water and discharges enough heat to supply the entire United States with electricity for 20 minutes. The Earth is alive with up to 2,000 storms at every moment of every day, which collectively flash about 100 discharges of electricity a second. More than 8.5 million bolts of lightning a day.
The whole atmosphere is very slightly charged, and the whole globe, it's called the global electrical circuit. When a thunderstorm develops, when a cumulonimbus forms, the updraft takes the air from near cloud base and near the ground, raises it up and takes it up into a level of the atmosphere where it doesn't belong, literally. You must have a vertical connection in the cloud that reaches high enough that the cloud has some part of it down to about 10 or 15 Fahrenheit. And when this water is injected very quickly in an updraft, the best way is in a thunderstorm, up into the top of a cloud, that combination of water and ice is very electrically unstable, and in order to stabilize the atmosphere, the lightning flash must be formed. Once that initiates, then the charge starts to come down, and it comes in 50-meter steps. It comes down, looks around a little bit, and says, is there something for me to hit? If there isn't, it comes down another 50 meters, looks around in all directions, it doesn't find anything to hit. So it comes all the way down to the ground in these little steps and little step leaders are called. And once it reaches very near the ground, objects on the ground are sending up streamers, and they're actually reaching out and saying, "Hit me." When that connection is made, then the visible light roars back up the channel, and that's the light that we see.
Each flash, which can run as long as 5 miles, while being only as thick as a twig, is driven by up to 100 million volts, heating the conduit of current to 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. The air around the bolt of electricity becomes superheated, producing an explosive clap of thunder with sound waves that move through the air at 720 miles per hour.
When I was 17, I was coming home during a storm that had a lot of thunder and lightning, and as I was coming around the corner, my Volkswagen got hit by lightning. And at the time it happened, I knew it was happening because you're surrounded by white. I mean, the most brightest white flash that you could ever imagine. And it just knocked my car just right off the road, off to the curb. And I sat there really shook for quite a while. When I could finally get out, I had a big old dinner plate size burn mark on the hood of my car right where it had been hit. And the force of that lightning being able to push a whole car, you know, just, it was amazing. It was just amazing.
Bizarre aberrations about the effects of lightning fill the record books. Holes sizzled into church bells. Potatoes baked where they lay buried beneath the soil. People talking on the phone, jolted by current transmitted down a phone line. Golfers swinging a club, attracting an atmospheric discharge. Umbrellas becoming instant lightning rods.
My most memorable experience in a hurricane was Hurricane Andrew. I was on a cruise ship, and at 5 in the morning, I was literally, my sister was with me, we were literally thrown out of our bunks across, you know, the cabin.
Most of the great storms of the world are born at sea. Hurricanes and typhoons are severe tropical storms. Within them, winds spiral inward toward the center of the storm, clockwise in the southern hemisphere and counterclockwise in the northern hemisphere. Light breezes, sometimes even the proverbial calm, prevail at the storm's center, where barometric pressures drop dramatically. Typhoons are hurricanes that occur in the waters of the Asian Pacific. Hurricanes are the most formidable tropical storms, with winds that reach 72 miles per hour or greater. Hurricanes can generate enormous energies, sometimes surpassing that of a 1 megaton nuclear explosion, more than 1 million tons of TNT. In southern Florida, when Hurricane Andrew slammed ashore the morning of August 24, 1992, it hit with winds reaching 145 miles per hour.
And the water was just pouring over the decks. The waves were so high, and we were just being tossed back and forth, and I don't think there was anybody there that didn't think that they wouldn't be dead, that the ship was going down. I mean, that was just the whole feeling, the noises, the way people were clinging to each other was, we're dying, we are drowning right now. And thank God, you know, it started subsiding enough that we knew everything was getting better.
A hurricane is quite a different animal. It typically generates from an instability area in the tropics, a group of thunderstorms or something along the tropics. And rather than having a cold front involved where it lifts the atmosphere and cools it and starts the generation of the storm, it actually feeds on warm water. It grows and matures, and as long as it's over warm water, it'll grow and grow and grow. As it moves over land, it loses its heat source, it loses its moisture source. The hurricane is also quite a large storm compared to, say, a thunderstorm. Thunderstorm is a couple of miles across, A hurricane is 100 miles across.
It was like we were a little bitty cork. All of a sudden, here's this force of nature that's taking this humongous ship, and it's just turning it and twisting it just like it was nothing. I mean, it just was like we and the ship were nothing. I mean, the storm, the act of God, whatever, was the most powerful thing that I had. Just unbelievable.
A hurricane has a lot of thunderstorms embedded in it, but it's a giant circulation center that spans a couple of 100 miles or 100 miles. And in that respect, it's similar to a large Pacific winter storm that moves across country, only it's warm instead of cold.
After it passed, it was just a numb feeling because you were so surprised to be alive.
Not all storms and their whirling winds are born at sea. Those that are spawned at least in part over the land can be every bit as awesome as their oceanic counterparts. Storms that begin over the land are composed of the same basic ingredients as those that start at sea: clouds, rain, lightning, and thunder. Even the most unusual and impressive effects of a thunderstorm are dwarfed by what follows when it grows a concentrated spiral of spinning power called a tornado.
I could see houses as it approached. It looked like someone had thrown a hand grenade inside the house, and they would just literally just explode. And when I saw the bank, the neighborhood bank, about a half a mile away from us explode, then I knew that we were in trouble. I knew that we were going to get hit.
I was coming home from my parents one evening around midnight, and there had been storms in the area all day, and it was raining really hard. And I was listening to the radio, and the news weathermen did say that there were some tornadoes in our area. And so I was driving home. There's a little country road, about 2 mile strip of country road to my house, and it started hailing really, really bad.
Many of us were huddled on the floor, and we were praying and saying and promising, and it was kind of exciting there for a while. There were some, actually, while we waited for the storm, we had about 15 minutes. Believe it or not, we had altogether about 15 minutes of warning, and some of the people were more apprehensive then than actually during the tornado, worrying about when the storm was coming, what would happen, and how would they fare. Was probably more worrisome to them than anything else, because when the storm hit, it was so fast. It was just there and gone in a shot.
The conditions for a tornado are provided by the Gulf of Mexico's warm breezes and Canada's frigid winds.
The temperature and the moisture fields are correct. And to get those fields together, we also end up getting a unique section of the winds. We'll have winds from the southeast at low levels and winds, say, from the west at higher levels, maybe at 10 to 20, 30,000 feet off the ground. And that combination of the winds and the right kind of temperature and moisture fields leads to the development of what we refer to as supercell thunderstorms, which are the most violent thunderstorms that are known to man and the ones which produce most of the violent tornadoes and almost always produce some kind of severe weather.
Tornadoes are born innocently enough. Warm, humid air rises from the ground in the morning, cooling into clouds sometime after noon, evolving into later afternoon, early evening thunderstorms. Gradually, a low-pressure area is created in the middle of the storm, which begins to draw air in from the underside of the storm. The residents of Tornado Alley, the nickname for a 460-mile strip of land stretching across Missouri, Kansas, Oklahoma, and the Texas Panhandle, know that a twister may be coming when they see a low-hanging mound of cloud accompanied by a downpour of greenish rain and large hailstones.
I turned and ran in the house and grabbed my wife, and of course we got in a closet. And immediately when I shut the door, it started, I could hear glass breaking. I wrapped my arms and my legs around my wife, and then it took the roof off. Then the bricks started flying in one wall and out the other wall. It was like being compared to being put in a paper sack and somebody shooting you with a shotgun. It was awesome. It was very frightening, to say the least. All I could do was just pray. The louder and the rougher it got, the louder I prayed.
It was pitch black dark, raining and hailing. And the wind was picking up and it's getting really loud. And my car was getting blown off the road. It would literally kind of pick me up and scoot me over. So I thought, this is getting really scary. And so I looked to the sky, and when the lightning would flash, you could see a funnel. You could see a tornado right in front of me. And so I just started praying that, first of all, my family was okay and that I'd make it home safely. I just knew that was the thing to do, because I knew that God was stronger than this storm could ever be, and that He's the one I needed to look to help me through this storm.
Hail is formed when water droplets coalesce around tiny particles of dust. As the drop falls through the cold air, it freezes. The size of the hailstones is determined by how many times the droplets circulate before they become too heavy for the winds to hold, and they fall to the ground.
Supercell thunderstorms are defined by having rotating updrafts that go through a significant depth of the storm and last for a long time. And by a long time, we're meaning maybe half an hour. So this storm itself is actually rotating throughout its entire depth, or most of its depth. One of the things it does that's very important is that it tends to help intensify the updraft, the vertical motions within the storm. And as a result, with a stronger updraft means it can support larger hail. Almost all of the very large hail, perhaps say larger than 2 inches in diameter, almost all of it is probably associated with rotating updrafts. And these updrafts may be going up as fast as 100 or 120 miles an hour or more within the storm. And essentially, a baseball-sized hailstone, the terminal velocity, or the velocity at which it falls at the same speed as the updraft going up, so that it falls out of the storm rather than being suspended, is about 100 miles an hour. So essentially, baseball-sized hailstone, standing out in that is the same thing as standing out in front of a major league fastball.
As updrafts spin into the cloud center, a funnel drops down and begins to darken as it picks up debris from the ground. Over land, tornadoes are invisible until they begin to pick up soil, becoming ominous black funnels. Over water, they appear as elegant waterspouts.
We believe that a process goes on something like this. Rotation develops at mid-levels in the storm, and this rotation is associated with the fact that in the environment of the storm, the wind changes with direction and speed over the lowest, maybe 10,000 feet of the atmosphere. And because of that, what we refer to as wind shear, there's a tendency for the air to be rotating around a horizontal axis. Much like if you threw a football with a spiral, it spins about the axis in which it's going. Well, if you can take that air that's spinning and tilt it upwards, it'll rotate around a vertical axis, and that's what we believe happens in supercell thunderstorms. And then once we've got significant rotation down to the ground, the final stage, the production of the tornado, is something else that's not completely well understood, but a large part of it may simply be what we refer to as the ice skater effect. As an ice skater spins with arms out, the ice skater spins slowly, and then as they pull their arms in, they begin to speed up.
Eventually, a tornado can spin whirling winds up to 300 miles per hour, packing a punch 100 times that of a 30-mile-per-hour wind. The funnel can move along the ground at a respectable 40 miles per hour.
A tree pulled up by its roots, very gently, laid down sideways and left, not a leaf stripped off of it. We saw the minister's house across the street, nothing done to it, but the house next door to it had the roof picked up, the four walls folded in, the pillars that were on the front porch folded on top of that, and then the roof gently set down with not a shingle missing off of it. A little bit further down the street, a car was picked up, and it was like the tornado was trying to clean up the mess it had made. it started scooping debris up underneath the car, and it got to where it was about 2 stories tall, and it set the car down on top like a chariot, like it made a hot fudge sundae or something out of all this debris. Because of the kind of world that we live in, that disasters happen. And it's like a reminder to me of God's awesome power. You forget his day-to-day creations. It's a powerful reminder of God's presence.
What is perhaps most fascinating about the tornado are the legendary stories which abound about the focus and selectivity of its power. Farmers tell tales of large farm animals being picked up and carried off, only later to be found alive along the twister's path. Twisters have been known to pick up kitchen cabinets full of dishes, or tables set for a meal, dropping the cabinet or table hundreds of feet away, leaving every dish unbroken. Pieces of straw have been driven nail-like into fence posts and telephone poles.
A lot of debris now, thunder. For that last CG, moderate rains. Ooh, blew up the transformer.
No wonder we look skyward with awe, and with a great deal of respect toward the forces that dwell there. With so much power behind each storm, it has been an understandable human preoccupation to find ways to predict the weather as far in advance as possible. Nowcasting, the name given to the usage of current weather data from periods of up to a few minutes, extending out a few hours, is useful for short-term events, like monitoring thunderstorm, hurricane, and tornado formations and directions. Forecasting is still important for a broad range of reasons. For the farmer, who needs to know when to plant crops. To the airline pilots and ship's captains who need to know what awaits them many hours or days away at an air or seaport. A wide array of technologies have been marshaled in our attempts to improve weather forecasting accuracy.
2, 1, 0, ignition, liftoff, 30 minutes after the hour.
The GOES satellites are what we call our nowcasters or our severe storm watchers. When you look at the weather that you see on the television, on your local news, that information comes from the GOES satellites. Since the GOES satellites are always in the same position, they constantly look at the United States and its surrounding oceans and give us all the information on tornadoes, hurricanes, severe storms, flash floods, and information like that. With the new geostationary satellites that we're now flying, we can track severe weather constantly. And what we do by tracking the severe weather, it aids us in picking up like a hurricane track or something else, so that we can plot on a map where that hurricane is going and constantly watch it. The big advantage to that is to be able to issue very, very accurate evacuation warnings and protection of health and property.
The pictures we normally are looking at are every 30 minutes, but for some very small-scale phenomena like tornadoes, we can look at the imagery every 15 minutes, even every 1 minute, depending on what we're trying to look at. Blue, in this case, are not quite as intense, but they are cold cloud tops, frequently with showers and thunder showers. Red is pretty intense thunderstorms, which you would expect right in the middle of the hurricane. And anything that's not color enhanced is warmer, and the ocean surface is fairly dark. And you can see in the desert Southwest, it's very dark on this particular enhancement curve.
We actually have antennas on the roof that can copy essentially all those satellites. Some of the data needs to be reprocessed. We also have communication lines with them so that if for some reason or another we can't get satellite data, and that would be that one of our computers is down or an antenna is down or something, we can bring it down through the communications line. Our function is to track those disturbances that look the least bit threatening, and they may show up in routine weather observations, or they may show up on a satellite picture, or a couple of other ways we might find out that there's something that arouses our suspicion, and then we track them, watch their development, and once they begin to develop, then we issue forecasts on them. We issue a 3-day forecast on their track and wind speeds. And then once they begin to threaten land, we issue a hurricane or a tropical storm as appropriate watch, which would be 36 hours before landfall, and then a warning, which would be 24 hours before landfall.
This part of the National Hurricane Center has a more varied group of products that it puts out. It puts out high seas forecasts for marine interest for the Atlantic and the parts of the Pacific, both north and south of the equator. Puts out aviation forecasts for a large part of the tropical Atlantic Ocean and the Caribbean, as well as a detailed aviation forecast for parts of the Gulf of Mexico. It also has aviation warning responsibilities, which are called SIGMETs, for areas in the Atlantic and the Caribbean and the Gulf of Mexico, as well as parts of the Pacific, for such conditions as severe thunderstorms, severe icing, severe turbulence, volcanic ash, and other conditions like that that might be very hazardous to aviation. We also put out several different map analyses and forecasts, including a large surface map of the entire tropical ocean from the Greenwich Meridian over to 160 degrees west. Between the hurricane work, the high seas forecast work, the aviation work, and our other duties like the satellite rainfall that we do for the Caribbean nations, there are millions of people living in our area of responsibility, and we're trying to take care of them as best we can.
We're putting in a network of 160 radars to be the weather radar input for all of the federal government, and that's 3 cabinet level agencies. We're using the Doppler principle. It's been used in defense to try to detect missiles and airplanes for many years, and we're now using this technology to look up inside the clouds and see the airflows. And for instance, if tornadoes is the threat we're talking about, we can see the rotation forming up inside the cloud. All of these radars work on the principle as you send out a pulse of energy, and a fraction of that reflects off of some target and comes back to the receiver. And the conventional radar knew only that, so it could tell you how much energy came back, and that could tell you whether it was light rain or heavy rain or maybe the possibility of hail, but it wasn't a great amount of information. Doppler radar not only gets that reflected signal back and measures the amplitude, whether it's light rain or heavy rain, but it gives you the wind velocity associated with that area where the signal reflected. So we can map those on a workstation and color and loop them, and we can see the wind flows and what the airflow is doing within the storm.
And the Doppler radar allows us to see velocities within the storm. So we can actually tell that the storm, what the airflow is doing within a storm, see that it's rotating, and see that it's one of these storms that is capable of producing significant tornadoes. The National Severe Storms Lab has operated a number of field programs in the past in order to go out and investigate kinds of storms, particularly tornadoes. In 1994 and 1995, the lab acted as the host for Vortex, the verification of the origin of rotation in tornadoes experiment, which is the largest project ever to study tornadoes in the world.
Well, it's 160.5, tornado on the ground.
And on that project, we put out 20 vehicles into the field and 2 or 3 aircraft with the idea of attempting to gather a tremendous amount of information about one particular storm on any given day. And so we would have vehicles in the vicinity of the storm trying to take meteorological measurements of the conditions that were in the environment and within the storm itself, so that we could learn more about the way that the storms form, the way that they behave, and hopefully be able to relate that to the kind of observations we can make on a routine basis to help forecasting.
Spotting generally evolved out of protecting communities and keeping an eye out for communities. What I basically do is combine them. When I chase, I still perform the spotting function for the Weather Service or for sometimes for Oklahoma County Emergency Management, sometimes for whatever TV station. This is Newcastle, Texas, from the 28th of May, '94. Just after I got out of town and rounded this curve, here's this monster tornado hanging out of the backside of this storm. It was, a pretty big tornado. It was the biggest tornado I'd seen it, in my entire chase career at that point. I'm really not sure why or how that interest was formed, but it's been pervasive through my entire life. It's I can't stand to have a storm anywhere around and not be able to see it safely. So, and I want to see as many of them as I can, and they never get boring, and no two are the same.
Today's advanced technologies are still supported by many of the forecasting techniques that have been in use for decades. Three-dimensional snapshots of the atmosphere are gathered from weather balloons released twice each day from hundreds of locations worldwide. The balloons carry radiosonde, which measures temperature, moisture, pressure, wind direction, and wind speed at various atmospheric levels as the balloon rises. Regardless of the source of the information, from advanced radar systems to people observing storms in the field, data is gathered on a worldwide basis and fed into today's supercomputers. Three-dimensional numerical models are created by the computers, with the goal of studying the destructive forces generated by severe storms. The computers are able to simulate the complex airflows that occur within thunderstorms, tornadoes, and hurricanes. In this example, warm, moist, low-level air approaches from the southeast and is propelled into the existing updraft. Cooler, drier air enters the storm at mid-level from the south and west, sinking to the bottom of the downdraft. In this simulation, colored particles are generated by the computer so that an observer can track the complex flow of air in a storm. Orange particles represent warm, moist air as it rises. Purple particles represent cool, dry air as it falls. Here, meteorologists are able to study the rotation of the winds in and around the storm. Weathercasters look for patterns that might give birth to tornadoes in America's Midwest. Hydrologists look for ways to predict conditions that will lead to floods. Typhoon and hurricane watchers try to collate data that will save lives along coastlines and out at sea. Nonetheless, the causes and effects of weather don't reveal themselves easily. They surface occasionally, even randomly, then disappear, like the eddies and swirls of a stream. This is where the chaos theory enters the picture, as the eternal modifier of our ability to ever predict weather with 100% accuracy, or anything even close to that. Chaos devours predictive efforts. Gravity, waves, and other oscillations shake weather models out of synchronization. Forecasters only half-jokingly call the phenomenon the butterfly effect. The idea that a butterfly stirring the air today in London can transform storm systems next month in Manila.
Because of small things like that that can't possibly be replicated on a computer or in some sort of an atmospheric model, a lot of people believe we'll never harness the weather. That probably has some validity to it. There are so many things that drive the atmosphere and drive the weather that it will be very, very difficult to harness all those things. And even if we do, even if we model the atmosphere absolutely perfectly, there's still going to be some problems because we have to measure it perfectly in order to start modeling. And right now, no matter how good our instrumentation is, no matter how good our measurements are, there is error in that. So that predictability is something that's going to be a very, very difficult thing to achieve long term.
Isn't it reassuring, though, or at least humbling, to think that man will always have only a limited grasp of the details of the grand design of God's creation? One of the important discoveries we've made during the course of this program is that an understanding of the divine origins of creation can be reached through scientific inquiry. Indeed, it seems almost impossible not to perceive the handiwork of God in the elemental forces of the world once we embark on our journey of investigation. The undeniable evidence of divine authorship is everywhere around us. Even the most casual observer of the world can see the love and wisdom at the root of all creation. Many of the scientists we spoke with had their own deeply personal ways of appreciating their encounters with the awesome forces of God's creation.
The most memorable storm for me is April 26, 1991. It was a day in which there were several supercells that produced long-track violent tornadoes across northern Oklahoma on up as far as almost the Nebraska border. And I realized, probably maybe after watching that one for 5 minutes, that this was something that, however long I go out and look at tornadoes, I'm probably never going to see anything that's going to be bigger or more intense than this one. And that I'm going to have a better look at it. And so I realized at that point that this was just something to watch and to sort of just see, knowing that, you know, if I do this for 30 more years, it's not going to be bigger than that one was.
It's just a power that you can't find very easily anywhere else in terms of both, I guess, in terms of raw energy, and then also in terms of, I guess, just, you know, all the different forces at work in the way that they're combining.
Well, I've always loved meteorology and love weather and enjoy all types of weather and storms. I find it very challenging, but also very exciting, the fact that every day somewhere in the U.S. there's something pretty interesting going on. And if you're aware of the sky and just keep track of what's going on, wherever you are, there's always something interesting happening.
I guess the most interesting part of weather and weather forecasting to me is the power of the weather. How devastating the effects can be. How if we can predict those effects, we can perhaps save lives, certainly property. I read something recently about the power from a thunderstorm. The energy and the heat release from a thunderstorm could generate enough electricity to power all the homes around the world for 20 minutes. I think it's just astronomical what the weather can do and what energies it possesses. It's just a fascinating science to try to figure out what's going to happen with all that energy.
I'm just sort of intrigued by them and the way they work, and the way that man is subject to them and not the other way around. When natural forces go on a rampage, we're the ones who have to duck.
It's part of the fascination with weather for me that we don't know everything about the weather. I think I would be less interested in the weather if we knew everything about it. I think it's okay for there to be a master plan and a power greater than us that's really in charge, and we just know a part of what's going on. And I feel privileged. I feel blessed to know part of it and be able to work in this area.
At every moment of every day, God's powers are evidenced around the globe. As lightning setting a forest ablaze with cleansing fires that clear away dead brush, making way for new growth. As rain that waters the parched lands of the earth, carrying nutrients into all the plants of our fields and forests. As the life-giving fresh water of our streams, rivers, lakes, and reservoirs. And as the whirling winds that cleanse the air of pollutants and constantly circulate the waters of life around the great blue orb of Earth. And as it is now, so has it always been. Mankind has long witnessed the imprint of God's power in the natural world. King David describes a storm that twisted the oaks and stripped the forest bare. Solomon, a great naturalist of the Old Testament, observed that the wind blows to the south and turns to the north. Round and round it goes, ever returning to its course. These are the enduring images we can conjure when we consider and when we experience, as did David and Solomon, the power of the awesome forces of God's creation.